hierarchy. So first, I would like to thank the coordinator of this STTP, Dr. Vivek ji, the first year coordinator, Dr. P.N. Deshmukh ji, and principal of this institution, that is Suhas Kaur ji, for giving me this opportunity to speak to this wonderful August gathering of intellectuals. And today I'll be deliberating on the topic optical materials devices for solid state lighting. So with this, I would like to proceed further. And as you all know about, like even in this era of digitalization, energy crisis is one of the most pinning issue globally. And we have already come up with novel, advanced materials, but still there is a room for developing more and more novel and newfangled advanced materials, and so that we can address this particular issue, that is the energy crisis. And hence, R&D is gaining momentum in various fields in terms of energy. If you talk about like various energy harvesting and converting devices like solar cells, which harness the solar energy into the light energy, solar energy into the electrical energy. And even there are some other devices which can store the energy like supercapacitors, and there are certain devices based on this energy conversion, storing, and all these things. Particularly, I'll be dealing about this light emitting diodes and organic light emitting diodes, which falls under the category of energy saving devices. And the topic of today's agenda is going to be the optical materials and devices for solid state lighting. First, let us try to understand what exactly these optical materials are, and later we'll be going for the optical devices, and then we'll be knowing something about the solid state lighting, and we'll see how these optical materials and devices are correlated with respect to the solid state lighting. So first, starting with the optical materials, like these are the materials which can interact and even manipulate the light. So if you're talking about to which particular range of light these materials are going to respond, these materials are not going to respond to each and every spectrum, are part of the spectrum of this electromagnetic radiation. These materials are going to respond only to few components like ultraviolet radiation or the light, visible light, and the infrared light. So we'll be dealing much with these components later in the further slides. So these materials could be either solids or even gels, composites, and mesophases. So mesophases, if you're talking about, these are, we can say that these are the materials, or we can say they are belong to the state of matter where they particularly do not belong to the phase of solids or liquids. They are intermediate between the solids and liquids. As we know, the liquid crystals, we can say that these liquid crystals are in mesophase. So now what are these optical materials and what are they doing whenever the light is falling on that particular material? So if you consider glass to be the optical material in this case, so there could be 4 different phenomena which could occur depending upon, yes, it's not getting changed. Now, what are you able to see? Yes, maybe there is a lag. Yes. Slideshow is there. I made it slideshow. Now you can see. It may take time. I think it's visible now. I think it's visible now. The very first one? Okay, I think it will do, no? That is true. It will take time now to do all these things. So what are you able to see? How are you able to see my presentation? Now, is it on the second slide? The transmission, refraction, what are you able to see? Yes, the same thing. Maybe there is a time lag. It may take some time. I'll be changing the slide slowly so that it will be coped up, I think. Okay, we'll see for the next slide and take the necessary requirement or the action. Okay, so whenever we consider optical material, in this case, we are saying that it's a glass. So suppose if light is going to fall on this particular glass, just a minute. So if light is going to fall on such glass, and if light is not getting bended and it is just directly passing through that particular glass, we can say that this process which is going to happen here or taking place is said to be transmission. On the other hand, if at all when light is falling on that particular glass slide and there is a bending of light, it may be in any other direction, there is a bending, and this process is known as refraction. Suppose if at all it's not entering into the medium and it is reflecting back or bouncing back, we call this phenomenon as reflection. And the other thing, and the last one, is the absorption. And in this case, the material is going to absorb all the incident light, or partially it's going to absorb, and this phenomena is known as absorption. So these are the materials, as I'm saying, as I'm talking about the optical materials, and these are the materials which may undergo all these four phenomena whenever the light is incident on such optical materials. Now, if you consider the examples, as I said, glass is an example for an optical material. Similarly, crystals are also examples of optical materials. So in my presentation, I'll be focusing much on these phosphors, which are based on the semiconductors. Even polymers are optical materials. The liquid crystals, which we generally use for liquid crystal displays, are also optical materials. The anti-reflection coatings, which we make on the spectacles and even other optical devices, we call them as the optical materials. And the opposite of anti-reflection coating is the dielectric material, where in case of anti-reflection coatings, it's like we are not allowing light to reflect, whereas in dielectric coatings we want light to get reflected. So this also comes under the optical materials. So if you talk about the optical devices, so there are devices which can alter or even detect, depending upon the device which you are using, they are going to alter or detect the light for a variety of applications. Suppose if I consider an optical fiber, so it's a fiber or a waveguide where the light is going to enter into the optical fiber. It's going to undergo the phenomenon of total internal reflection, and this light is going to be guided along the length of this fiber. And then comes the photodiode. If you talk about this, it's going to sense the light. It's going to work as a sensor. It's going to sense the incident light, and the sensed light is being converted into electrical energy. And same is the phototransistor also. But when we compare photodiode and the phototransistor, the amount of light being absorbed by this material will be more if at all we are considering the transistor, because the size of the transistor is more when compared with the diode, and the area which get exposed to the light is also more in case of phototransistor. And I already said, yes. So I'll do one thing. Just a minute. I'll do one thing. Just a minute. What you can do is you can open from your side. It is true, but it will take time. Wait a minute. Now are you able to see? Slideshow. Ah, okay. So I'll be starting from here. Okay. Are you able to see today's agenda? Yes, yes. Okay, fine. Huh. So I'll be proceeding further. So today's agenda would be like I'll be discussing basically the phosphors based on the semiconductors, which works as the optical materials, and I'll also be discussing about the optical devices, which are like light emitting diodes and organic light emitting diodes with respect to solid state lighting. So first, in order to understand the role of these optical materials and devices in solid state lighting, so first let us try to understand what exactly lighting is and how it's like evolved and how we are landing on this solid state lighting applications. So first, when we talk about the lighting, it's nothing but the purposeful use of light to attain realistic visual effect. As you all know, the natural light source, the sun, is going to be there only on the daytime, and we'll be able to perform the task only during the daytime if at all we don't have the artificial light sources, and hence the necessity of artificial light sources have come into existence. And because of these sources, we are enabled to enhance our task performance, and even we can extend our work time and even work towards the night time also. And now it has become the basic need along with our food, shelter, and clothing. So we can classify this lighting into three different categories. The first one being the task lighting. Suppose if at all we are using the lighting to perform certain tasks like reading, sewing clothes, or if we want to do homework or even surgical procedures, the lighting which we use would be totally different. And these are used only to perform certain tasks which are really important, and we are interested to do the things very keenly, interestingly. So that lighting is known as task lighting. When you talk about accent lighting, it's just for interior designing and the decorative purposes. And if you talk about ambient lighting, it's a general purpose lighting, and it can be accomplished with the fixtures which we can be arranging to the walls or to the ceilings. And even the track lights and the lanterns comes into this category or falls into this category. If you talk about this color rendering index, this is known as color rendering index. So suppose if you see the image with color rendering index 62, you're not able to identify the exact color of that particular item which is exposed to that artificial light. If at all you see the second diagram, it is appealing and it looks natural. So more is the CRI number, then more will be the clarity and visibility of the image perfectly. And hence we need to select the type of lighting depending upon the application or the usage of the individual. So first let us talk about the artificial lighting, how it has been evolved. So earlier days, the work used to be done only within the daytime because artificial lightings were not set at that particular point of time. Later started with the fire and then the kerosene lamps. And as you know, the kerosene lamps are going to deteriorate the health of the persons with respect to the lungs, and hence they are not like recommended. And later came the candles and then the filament bulbs and the tungsten filament lamps, we can say. And then came the fluorescent bulbs, compact fluorescent bulbs, LEDs and LED bulbs, and now it's an era of organic light emitting diodes. First, let us try to understand each and every one of this particular evolution and see how they are going to change or leading to certain advantages and certain disadvantages first, and then we'll see how LEDs and OLEDs are being replaced in their first place. So now if you talk about the incandescent lamps, they have the appreciable lifetime, and they are only suitable for small areas. And though they have good coloring index, there are certain limitations that we'll be seeing later. And you don't have any toxic materials even if you dispose this lamps after their life is over. And even if you consider their life, it's going to be 750 to 1000 hours. And these were the traditional lights which we earlier used in our previous decades, we can say. And they are generally operated at normal voltages. The main problem of this lights is that the conversion efficiency is less, like only 10% of the conversion. So we are providing some electrical energy and we are getting the light energy. So whatever electricity is provided, so among that, say it's 100%, 100%, only 10% of that particular energy is converted into visible light, and the remaining 90% of light is wasted in the form of heat. So even if water spills on that particular incandescent lamp, by mistake, it's going to burst. And though it is least expensive, but the bill is going to be high. And hence we can say that it's most expensive to operate. They're also useful for lighting large areas. So as I said, it could be, if at all the room is very small, it will be lighting up the complete room. But if at all the room is large, we need to have n number of light sources in order to illuminate the room. And they are fragile, easily breakable. So if you talk about the limitations of this, if you see this, so now if at all I'm going to measure the intensity of this light at a distance 0.5 meter from this light source, so the intensity of light which is being emitted is, say, 40 lumen per meter square. Suppose if I measure the distance once again after half meter, then the intensity is reducing drastically. So the intensity of this light emitted by this incandescent bulb is more intense when it is closer, when the area is close to that bulb. And as the distance increases, the intensity is going to decrease. And this is how the inverse wave law can be demonstrated with this incandescent lamps. So now if you talk about the sun as well as the filament bulb, so they are going to give you the same sort of emission. The color which we can observe out of this bulb is matching with the sunlight color. So now if you talk about the demonstration of incandescence in sun and filament of an electric bulb, you can see that the intensity is going to vary. So now if you see from bottom to top, if you can see with GR, so green, yellow, orange, red, and it's going to be the darker red. So more is the wavelength, more is the temperature, and more is the intensity. So if you see here, the following curves, in these curves, the energy loss is there in the form of heat, and this is known as color correlated temperature. And how closely it looks, color correlated temperature means that it's something like temperature. At that particular temperature, say sun, so it has certain temperature, and that at that particular temperature, what would be the wavelength emitted by that particular sun, and what will be the way we see the object. Similarly, if at all we are seeing some other objects, so how naturally they look, that is something measured in terms of temperature, and it's known as color correlated temperature. And now if you talk about the linear fluorescent lamps, so because of certain disadvantages, we have come up with the linear fluorescent lamps, and they generate cool light and even the white light. So the incandescent bulb, which we talked earlier, is going to release only 10% of energy in the form of light and 90% of energy in the form of heat, and hence we call it as hot emission. Whereas the fluorescent bulbs are going to give you the cool emission. No heat is being, or we can say no much heat will be released in this process. And they use the phenomenon of fluorescence to generate white light, and the efficiency is going to be 50%, which is more than the incandescent bulbs. And they are about 3 to 5 times as efficient as incandescent bulbs, as I said. And the lifetime is going to be more as compared to the incandescent bulbs. And that lifetime is going to be around 7 to 10,000 hours of use. But the limitations are like they are fixed only to the walls. They can be fixed only to the walls, and hence they are going to occupy a lot of space. And even if you turn it on, the switching time is more, and it takes time to turn on. And even the bulbs contain mercury, and if at all, if its lifetime is out, if at all we try to dispose it, you have mercury in it, and it is a hazardous to the environment, and it's a waste which is creating the environmental hazard. So, and hence these are not a preferable form of lighting, and even they are easily breakable. And hence the next evolution to solve the problem of space, there came the compact fluorescent lamps. So as the linear fluorescent lamps, they too consume less power. They, as compared to that, they take very little time to warm up and reach to the fullest brightness. And These lamps lower the greenhouse gas emissions. They are very costly, but they have a longer lifetime. These bulbs are a bit costly, but the lifetime is going to be more. Again, the problem remains the same because they are also compact fluorescent lamps. They have the toxic mercury in that, and hence disposal would be a hazardous to the environment. So these CFL bulbs exhibit optimal performance only around 20 degrees centigrade. And with the increase in the temperature, the efficiency is going to be less, as even if you go for lower temperatures, the efficiency is going to affect. And hence there is a limitation in this also. The very first limitation here is the toxic mercury which they have. And the second thing is only at one particular temperature they are going to work effectively. And if you increase or decrease the temperature, it's going to be, the efficiency is going to be less. And hence comes the solid state lighting. So now when we talk about solid state lighting, so it's nothing but the new lighting technology where the illumination is by solid state devices like semiconductor devices. So solid state device, because it is known as solid state device because they are made up of semiconductor devices. LED is a solid state device because it's made up of a semiconductor. Even the organic light emitting diode, it's also a solid state device because even here we are using the semiconductors. And even some of the polymers are, they're also like semiconductors, and hence we call all these materials to be the devices to be the solid state devices, and the lighting obtained from these devices is known as solid state lighting. So now let us try to understand why we are interested in this solid state lighting. So there are many advantages of solid state lighting. The lifetime is going to be more, as you have seen in the LED bulbs or the LED lamps. The lifetime of these lamps are more. They are very secure. They are not going to give you any shock. They are toxic free. They don't have any mercury. They are flexible light fixtures. So with OLEDs, we can go for the flexibility. We'll see that in short while. So they are energy efficient. We can even recycle them, and the emission given by them is very cool. And we can say that since they don't have mercury within them and they are going to give cool emission, they are recyclable, they are energy efficient, we can say that they are eco-friendly, and we can easily maintain them, and the lifetime is more, and we can make them to be versatile in designs. They are cost effective, and since they are eco-friendly and energy efficient, we can say that this solid state lighting is going to be the green technology, and it has the potential to revolutionize the upcoming lighting industry. So now let us start with the light emitting diodes and see how they work and what are the advantages of that and how they are going to be different from OLEDs and why OLEDs are emerging. And let us see much more about those things in the next few slides. First, starting with the LEDs. We can consider this invention of LEDs to be the greatest invention of 20th century. They were invented by Henry Joseph Rold in the year 1907. So they just operate in the forward bias. So what do you mean by forward bias? It's like only the positive terminal of the battery is to be connected to the P-type semiconductor, and negative terminal is to be connected to the N side of the semiconductor. Then only it's going to emit light. So earlier, these LED devices are only used as indicators or even the 7-segment LED displays. But later, with the efforts of the researchers, there has been LED bulbs and LED TVs, which we are using right now. And if you talk about these LEDs, they are, as I said, they are forward biased PN junction diodes. And because of electron hole recombination, the light is emitted, provided we need to supply certain amount of energy to that. So now they work on the principle of electroluminescence. It's nothing but the process in which the electrical energy is going to be converted into the light energy. If you talk about how to identify the LED device and make the connections of it, the circuit symbol, this is the circuit symbol. The arrows here just indicate that the light is emitted out of this device. And these are the two terminals, and this is known as a cathode and this is anode. And if you can see, the terminals have different lengths. So the shortest one is called the cathode and the longest leg is known as anode. And even so, this is going to emit only a single color. Similarly, there are bicolor LEDs, there are tricolor LEDs. So here, if you can see, there is a common terminal which is denoted with positive, and there are 3 more terminals RGB. So depending upon the requirement, we can go for the red LED. The same LED can be used for 3 different colors depending upon how we bias it. And that is how we can identify and use this bicolor and tricolor LEDs. And there is a question, and I would like to get the answer from you. I just want to know what would be the energy gap of the semiconducting materials if at all it want to work as an LED. Any one of you can answer it? Yes. Okay. So the semiconductors, see, if you can see, not all semiconductors can be used for this purpose. Only there are certain semiconductors whose energy gap is lying in between 1.7 to 3 electron volts. So only those semiconductors whose energy gap is lying between 1.7 to 3 electron volts can be used as LEDs. Because if you consider the energy gap and wavelength relationship, we can easily calculate what would be the wavelength of the light emitted if at all that particular material is used as a semiconductor. So substitute the value of energy gap. Say if it is 1.7, substitute it here. We can obtain the wavelength of the light emitted by that particular LED. So here specifically, I'm saying that the LEDs are going to emit light only if their energy gap lie between 1.7 to 3 electron volts. Let us try to understand much. So if at all you consider germanium and silicon, the energy gaps are less. And even if you consider 1.45 electron volt energy gap material, which is nothing but the gallium arsenide, and if you try to calculate the wavelength of it, it's going to emit light whose wavelength is around 8,500 angstroms. So this is not going to fall in the visible region, and hence will not be able to see the light if at all we use the semiconductor of this energy gap. And it will be emitting light or emitting radiation in infrared region. So now that is why I'm trying to say that only those materials whose energy gap is between 1.7 to 3 electron volts will give you the light in the visible region. So if at all you consider the gallium arsenide phosphide like 1.9 electron volts, it's going to emit the wavelength which falls in the visible region like this. So we need to select the materials depending upon the energy gap. We can choose the wavelength of that particular LED. So if you talk about the construction, you have anode at the top and you have the cathode at the bottom. Usually gold is considered to be the cathode layer, and you have an n-type substrate, and you have the active region here, and you have a p region here. It's nothing but a p-n junction diode. So this is a sort of depletion region, and this is said to be the active region. And the n-type semiconductor is going to have electrons as a majority charge carrier. Similarly, the p-type semiconductor is going to have holes as a majority charge carriers. Due to concentration gradient, the holes are trying to move towards this side, towards the active region, and electrons are trying to move towards active region. And in this process, this active region is the depletion region here. Closer to depletion region or within the depletion region, there could be the recombination of the charge carriers, the free electrons and the holes, and the recombination is going to give you a light, or is going to emit a photon, which is nothing but light. And this electron hole pair is known as exciton. And this is how the electrons and holes are getting recombined, and they are giving you the light. Depending upon the energy gap of the material, the color is being changed. So now there are certain requirements for LED to function effectively. So first, our interest is like much light must be emitted out of the device, right? So now if more light is to be emitted out of the device, what is required? More recombinations are required. So if more recombinations are required, what is required? So more number of charge carriers are required. So more the light required, more should be the recombinations. More the recombinations required, more must be the electrons and hole pairs. And in order to have more and electron hole pairs, we need to dope the semiconductors heavily. So heavy doping is going to lead an intense light which is coming out of that LED. And the second thing is the recombinations are going to take place everywhere around the active region, but we want to confine the light only in one particular region. We don't want light to be wasted in the other regions, other directions, at the bottom or the left side or the right side. So we need to dope it asymmetrically. What does asymmetric doping means? See, if you can see, the p region is smaller in size or in thickness, and n region is thicker. And even n type is heavily doped and p type is lightly doped. So more the electrons will move towards this region, and the electrons and the holes which are in the p region needs to travel a very shorter distance, and they are going to recombine here. So because the recombinations are taking place at the very surface of the device, most of the light is going to emit, and it would be in one particular direction. So almost all light should emerge from the device. So that is why the p region is made thin. So even we want to protect this p-n junction from the moisture or the contamination, and hence we want to go for the encapsulation, and hence you can see like dome-like structure on the LEDs. So this is nothing but the encapsulation, and this avoids the contamination and moisture. So in order to encapsulate, we generally use a clear epoxy resin, and the refractive index of that material lies in between the refractive index of the semiconductor and the air. And there is one more condition to be satisfied, like angle of incidence must be angle of incidence must be greater than the critical angle. Then only the total internal reflection is going to take place. But we are not interested in total internal reflection, and hence we are making the angle I less than the critical angle, so that we'll be having the reflection outside. So these are the characteristics, VI characteristics of LED. So depending upon the color, the barrier voltage would be different. So this is how the VI characteristics of an LED looks, and this is how the LED lamp looks. So these are the parts of the LED lamp. So this is the base, and this is the part where we fix to the fixture, and this is the LED connector which is going to connect the base and the driver, and driver is the one which is going to supply is going to power up the LED, and this driver is going to convert the AC to DC, and almost during the process of conversion, certain amount of heat would be released, and hence the heat sink is going to protect the device from damage. So the heat sink is provided here, and you have an LED panel over here, and you have certain square type structures on this LED panel. They are known as surface mount devices. These are the LED chips, and these are being mounted on this particular surface, and next comes the globe structure, and all together forms the LED bulb. And there is one more kind of LED lamp. Maybe most of you have not seen this. These are the filaments. This just looks like a filament bulb, but actually these are not the filaments. They are known as they are mainly made up of the phosphor. So if you can see here, this is the one of the filament, and it is after electrically powering it, it is how it looks. And if you talk about the construction of this LED filament, you have a glass substrate, and you have two electrons on inner side. So one being the anode and the other one being the cathode. And inside the glass substrate, you have a glass substrate, a glass here, and the chips are being arranged here. So red chip is arranged here and blue chips. You can see like there are few blue chips and red chips, and they are being bonded onto this glass, and you have a phosphor coating on this. So whenever it is electrically switched on, this phosphor is going to excite these LEDs, and that is how it's going to glow. So now the question arises, why we are talking about LEDs and how they are advantageous. So if you talk about LED light bulbs, their lifetime is more like 1 lakh hours, and the amount of energy that they are going to convert is around 20%. As we have seen in the incandescent bulbs, it's only 10%. And like fluorescent lamps, they don't have any UV light, and they are recyclable. They can be recycled, and there is no toxic elements which are there in this LEDs. And the amount of energy conversion is going to be 90 to 90%, and they can operate even in the colder regions, and hence we are preferring this LEDs. So now, if you compare the amount of energy wasted in the current lighting system, if you talk about the traditional bulbs, if it's a suppose if you consider that approximately wattage needed to produce 1600 lumens. If at all my target is to produce 1600 lumens, I need to use 100 watts bulb. So for this, if you talk about halogen incandescent bulb, only 77 watts is required. If you talk about compact fluorescent lamp, only 23 watts is required. And for LED, it's the minimum, that is 20 watts. This is how the energy is saved with the help of this LED usage. So now let us go for the merits. As I said, they can be operated at very low voltages. They require very heating, require They doesn't require any heating or warm up time, because as if you can see in tube lights, they take time to warm up and then they flicker for some time and then turn on. But that's not the case with the LEDs. They are faster in action. They can be switched on and off very fastly. They are smaller in size. They are even lighter in weight. So they are less fragile than glass, and they're not affected by any mechanical vibrations. The lifetime is going to be more for that. And the applications, if you're talking about, we can use them for LED segment displays, 7-segment displays. They can be used as indicators. Even we can use infrared LEDs for optical fiber communication. They are being used for general lighting. Nowadays, they are preferred. And even the traffic signals, the solid state video displays, the TVs which we are seeing now are LED TVs, are like, we can say, the OLED TVs. And these are the applications of LEDs, and the picture itself explains about the applications. They are the LED rope lights, they are lantern string lights, the signages, traffic lights. These are the TVs, light, and the car accessories, that's the bulbs. And this is the solid state lighting. So solid state lighting is nothing but the lighting which is used for domestical application, and this is done with the help of solid state devices. Then it is known as solid state lighting. So if at all you arrange number of LEDs in such a pattern, we can even get the LED bulbs. So now this is how a solid state lighting of a room. So most of the houses which are built recently have the false ceiling, and LEDs are the main components of that ceiling, which gives an appealing effect for this interior decoration. So now let us talk about the limitations also of these LEDs. So before that, as you know, this is the most modern and best environmental lighting system in the visible range. They have very narrow spectral bandwidth, and the lifetime is around 50,000 hours, and they're capable of generating white light. So we'll see how white light is generated. They can even consume less power. The point here is that the LEDs cannot be spreaded to a larger surfaces. They are point sources. We need number of sources to be arranged so that the intensity would be maximum, and even they are not flexible. And hence we are going for the next part of LED, that is nothing but the organic light emitting diode. The only difference here is the material which we are using to make an LED. In the initial case, we used to have the inorganic material, and here in this case we are going to use only the organic materials, which are like the small molecules, polymers, or dendrimers. So why do we need these OLEDs? We'll just have a look on it, and that will be further moving ahead with the materials for OLEDs. So they are efficient than the incandescent bulbs, give off better light than the fluorescent bulbs. So we are just comparing how they are superior with respect to incandescent bulbs, how they are superior with the fluorescent bulbs, and even they are versatile with the LEDs. Sorry, displays faster, brighter, and even they draw less power. And the very important and the most appealing part of OLEDs is that they are malleable, they are flexible, they are rollable, and hence this makes it versatile from other lighting systems. So, and even it is easy to fabricate. So now let us try to understand what's so great about these OLEDs when we compare with the other lighting systems. So as compared to other lighting systems, the response time is very fast, and they offer very wide viewing angle. Means whenever we are operating a laptop, if at all we are seeing it directly, we can see the image very clearly. But if the viewing angle is changed, like if you are seeing that particular object from different angle instead of looking it straight, so the blurred image can be seen, and that is nothing but viewing angle. So that is the case in case of LCD. But whenever we have OLED TVs, or even the LED TVs, the wide viewing angle is given. So even if you see from different angle, apart from even 360 degrees, I can say 180 degrees, the image remains same. The better clarity from any angle. So the color reproduced by these displays are going to be exceptional. They can be operated at lower as well as higher temperatures with good contrast and brightness. They are extremely thin and even lighter in weight. The thickness of that particular device is almost 1 micron or 1 micrometer, we can say. They consume less power. As I said, they are flexible because they can be printed onto any medium, and we can see the rollable displays in the future. So if you talk about the structure of OLED, that's the anatomy. So earlier devices used to have only a single layer between the anode and the cathode, and the region between the anode and cathode is known as emissive layer. So in order to increase the efficiency of this particular device, so we have added some layers over here, like electron transport layer and the hole transport layer. So these are the layers which are going to enhance the transmission of electrons or transport the electrons and holes, and increases the recombinations, and hence more will be the efficiency of the device. So after that came a multi-layer device, a 3-layer device, and then a multi-layer device which has number of layers, and which we'll be seeing now one by one. So the first one is the anode, which is going to be transparent. So if you see the image, we are talking about these layers, all these layers. So we have a glass substrate, and this is the anode, and that is what we are trying to understand now. So it's going to be transparent, and it's going to have a high work function. Generally, indium tin oxide is used because it has high work function, which is in between 4.5 to 4.7 electron volts. Apart from its work function, so there are many advantages of using the indium tin oxide. It's transparent to visible light, it has good conductivity, and it's chemically stable. And apart from this ITO, there are many other anode materials which can be used, and they include the aluminum doped zinc oxide, which we generally call it as AZO, and fluorine doped tin oxide FTO, and the transparent conductive oxide TCO. And even recently, graphenes have gained momentum, and they are being used as anode material for OLEDs. So this is the other layer which deals with the whole injection materials. So these materials have high mobility, and they can block the electrons, and they can make holes more mobile, and they have high glass transition temperatures, and these are the organic materials which are generally preferred for materials as hole injection layer. And then comes the hole transportation layer, and these are the materials which are generally used, and the hole transport layer is going to increase the mobility of the holes, and this material should have low ionization potential, low electron affinity, and even it must be thermally stable and electrochemically stable. Only those materials which satisfy all these requirements can be used as hole transporting materials. And then comes the emissive materials, so which we are talking about, the optical materials. So these are the materials which should have high efficiency, they should have good lifetime, and offer good color purity. And because of this reason only, we are going to use these small molecules and conjugated polymers and the conjugated dendrimers. So these are the emissive materials which are generally used, and these are responsible for emission of light. So depending upon their energy gap, the color of the light varies. And if you talk about small molecules, they are known as small molecules because the molecular weight is low, and they are generally deposited by vacuum evaporation techniques or by sublimation process. So if at all we are going for an OLED device using the small molecules, the thickness is going to be less than 1 micron. And if you say about OLED, it means that SM OLED, that is small molecule OLED. If you talk about PLED, it means that it's polymer OLED. So if you simply talk about OLED, it means that it is made up of small molecules. So now if you go for polymers, they lead to PLEDs, like polymer LEDs. And the techniques which are used to make these PLEDs is by inkjet technique, spin coating technique, and the casting technique. Since we are using polymers, we can make these polymer substrates. We can choose the polymer substrates and coat these materials and make them flexible. And since they are polymers, they are cheap, and it is easy to fabricate. And if you talk about dendrimers are nothing but the branched molecules. They have the cores, and you can see here the branches. Branches are also known as dendrons, and the surface group. So the core is going to define the electronic property, and it is going to decide what color will be emitted from this device, if at all you are using this dendrimer as the emissive layer. So the world's most efficient solution processed LEDs are made with this dendrimers, and the quantum efficiency of these devices is around 16%. So we can either use the small molecules, we can use the polymers, or we can use the dendrimers. And if at all we are making these devices, we are using these material to make the OLED devices. They are known as organic light emitting diodes. So, and if you're till now we have talked about the whole transport and the whole injection layer, and now we are talking about the electron transport layer and the electron injection layer. So if you talk about electron transport layer, so they should have good transportation. They should transport the electrons. They should increase the mobility of the electrons, but at the same time, they want to block the holes. They don't want the holes to enter in that particular direction. And they should have higher electron affinity and the ionization potential. And these quinoline-based complexes are mostly used for electron transport layer. And if you talk about cathode materials, it should have low work function and the low threshold voltage. And these are the materials which are generally used for cathode materials. And now let us see how the light is being emitted out of this device. We have understood the different layers. So this is the anode, which is nothing but indium tin oxide. We need to have a whole injection layer. We need to have a cathode. We need to have an electron injection layer. So now, whenever it is energized, the electrons move from cathode to the electron injection layer. Similarly, the holes are going to move towards the hole injection layer, and these holes will be transported towards the emissive layer, and similarly the electrons will be transported to the emissive layer. And here the electron and hole is going to form an exciton, and the recombination of which is going to emit a photon in this direction, and that is how the light is emitted. So whenever the recombination is taking place, depending upon the energy gap of the material, either we can have the blue color or the wavelength corresponding to green, or the wavelength corresponding to the red, or any other color can be emitted. So now the recombination should take place only in the region which is known as the emissive region. If you can see, if at all the recombinations are taking place at different places, then the efficiency of the device would be less. What we are trying to do here is we are confining the recombinations to one particular region, and that is the emissive region. Here itself, we are making it thin, and we are having some other layers on either side of it, so that the electrons and holes are going to recombine within this particular region, and you have some light in one particular direction. And now, as we have the formula, as we have studied in LEDs, the same thing is going to be applied here also. Here also, the wavelength of the light depends upon the energy gap of the material which we have chosen. And many countries are working on this OLEDs. R&D is going on the manufacturing, and these are the companies which are working on it. So if at all this many companies are working and this many countries are indulged in the research of OLEDs, definitely we are going to have this OLED lighting in the near future. So let us try to understand the differences between OLEDs and the LEDs. So similarities are both have the anode and cathode, and electrons and holes are going to move toward the device, and the light is emitted. But the difference is that the emissive and conductive layers are made up of organic materials here, whereas here it is of inorganic. Here the substrate cannot be plastic, and here the substrate can be plastic, and hence because of this reason, these OLEDs are going to be flexible devices. So now let us try to understand what are the different types. So top light emitting OLED, which means that it's going to emit light only from the top, and nowhere the light is being emitted. So if you have a thin film transistor circuitry which is going to control the on and off state of the pixel, and the light is emitted only in one particular direction, as the name suggests. Similarly, if you talk about bottom emitting OLED, the substrate is at the bottom and light is also emitted to the bottom. Even here we have the thin film circuitry which is going to control the pixels. And you have one more type which is known as transparent. It's transparent in the sense it is going to allow light to pass in both the directions. Like either it can be emitted either night. So it will be emitted from the top as well as at the bottom. From both the directions the light is emitted. And hence we call it as the transparent LED. And we are interested in this white OLED because of these reasons we know that. So if you can see the solid state lighting here, the rooms of our houses in near future would be looking like this. So if at all we use these OLEDs for solid state lighting, instead of the bulbs, we can just coat. So this is the advantage of OLED. Instead of using the fixture, the bulb, so we can coat the phosphor onto the larger surface area, and whenever we switch the light on, the anodes and cathodes will be there, and they are going to emit the light in this fashion. And this type of technology is going to minimize the space required for the lighting, and even the fixtures are not required in such solid state lighting with OLEDs. So there is one more type of OLEDs which are known as stacked, which means that the pixels, instead of being arranged horizontally and vertically, they are on top of one another. Like RGB subpixels are placed on one another, and this is going to improve the resolution of the display. So this type of displays are हेलो। हाँ, एक्चुअली क्या हुआ, लाइट बंद हो गया तो नेट का प्रॉब्लम आया। हाँ, ओके। आर यू एबल टू सी नाउ? Visible? Hmm. Sorry, I was not knowing that I am not online. Okay, slideshow. Okay, I was talking about the process of luminescence. So, as if we have studied in the laser, the emission of light is because of the movement of electrons within the substance. So, whenever you have an electron in the ground state, whenever light is incident on such electron, it is going to gain certain energy, or it's going to absorb that energy, and that energy is utilized by this electron and it jumps to the higher energy state. So now this higher energy state is not going to allow it to stay for a longer period of time. Okay. Is it okay? Huh, huh. So now the electron which has absorbed certain amount of energy is now jumping into the excited state, and the lifetime of this electron here is not going to be much, and it's going to come back to its initial state, that is the ground state, and light emission is going to take place. And this emission of light, if it lasts for 10 power less than 10 power minus 8 seconds, it's known as fluorescence, or if it is greater, then it's known as phosphorescence. And now this is how we generally explain the emission of light. Suppose if the emission of light is accompanied with heat, then it is known as incandescence, as if it occurs with incandescence bulb. And if it is not releasing any heat, then it is known as luminescence. And in luminescence, we can excite that particular material either with light or with some other external energy. And suppose if it is excited with light, then it is photoluminescence. And light emission ceases immediately, then it is fluorescence, that is within less than 10 power minus 8 seconds. If it is greater than 10 power minus 8 seconds, it's known as phosphorescence. Suppose if the luminescence is, light emission is because of some ionization radiation, then it's known as radioluminescence. If it is because of the electrical current, it's known as electroluminescence. If it is because of chemical reaction, then it is known as chemiluminescence. And if it is on based on the temperature, then it is known as thermoluminescence. If at all it is based upon some mechanical force like stress, pressure, sound, friction, then it's going to have some other type of luminescence. So in this way, so a material can be exposed to different energies, and accordingly the light can be emitted. So these are the materials under UV light. So if you can see, when UV light is being exposed on such material, it looks green. So it's a property of that material to emit green color. Similarly, the red color and the white color. And now if you want to have solid state lighting, it's generally white, and hence we need a combination of RGB. So we need a red, green, blue in appropriate proportions to make white. Or we can have an yellow phosphor, and it is to be excited by blue chip, a blue LED chip, which is going to give you a white. So again, the same thing is repeated. So we can have the combination of blue, green, and red in appropriate proportion. Or it could be yellow phosphor excited by blue LED, or it could be UV LED which is excited with R, G, and B, all the three colors. So now we have prepared certain rare earth based beta diquinonate phosphors. We have chosen these rare earths because they are going to give narrow emission, they have longer lifetime and the stroke shift, and they are known as beta because the position is at 1 and 3. So these are red light emitting diodes. So I'll be skipping the things which are not more relevant. And now these are the beta diketonate complexes we have synthesized, like EU TTA thrice bipy. This is europium, and this is phenyl trifluoroacetone. This is bipyridyl. Okay, so this is the other complex which we have synthesized, and I'll be letting you know how it is being synthesized. So now initially the europium chloride is taken, and the ligand which we have considered here, like the ligand, if I talk about TTA is a ligand and The other ligand which we have used in some other synthesis is DMH. This is the secondary ligand. This is bipi in this case, and here it is going to be phenyl. So even if you consider EU-TTA thrice, it's also going to be a password. But since it's an organic material, so this is inorganic. We can actually say that it's a hybrid complex. It's a combination of inorganic and the organic ligands. So now even this much will do, but it's volatile, and hence to improve the volatile nature, so it's non-volatile, and hence to improve the volatile nature, we are adding the secondary ligand, which is bipyridine here, and it is phenanthrolene here. So now the ligand, the first ligand is taken, and both are mixed, and the pH is to be adjusted. Initially, whenever we mix these two, the pH will be generally around 3 to 4, and we want to adjust this pH to 7 or 7.5 by adding the KOH, diluted KOH dropwise, and we want to keep this solution onto the magnetic stirrer. We want on the hot plate, and with the magnetic stirrer we are going to stir it, and once the precipitate is formed, so we are supposed to stir this for 1 hour, and the precipitate is formed. This will be filtered, and we are going to get a complex like this. It's nothing but the phosphor, and when we are exposing this complex to ultraviolet light, we can observe that because we have used europium, it's going to emit the red light. Similarly, the other complex is also prepared. So these are the structures of the complexes which we have prepared. And here the emission is because of the antenna effect, which means that this is the structure of the complex which we have prepared, like EU-TTA thrice bipi. So the europium here is the metal ligand, and you have one ligand here, like this is bipi, and this is nothing but TTA. So this is thrice, taken twice. So now the europium itself cannot emit energy, and it is getting energy through transfer from these two ligands. So if you can see here, bipi is also transferring its energy. Similarly, TTA is also transferring its energy like this. So because of this energy transfer, the emission to this metal ion, the emission is possible. And this effect is known as antenna effect, and this happens only under the external energy availability. So now if you talk about the PL spectra of this, we have taken out the photoluminescence spectra, and you can see that it has been excited at 381 nanometer, and the emission wavelength is around 640 nanometer. And you can see small peaks over here, and these are the characteristic peaks of the europium. So if you see 581 nanometer here, so it is because of the transition of from 5D0 to 7F0 of europium. Similarly, 592, 598 belongs to 5D0 to 7F1 transition, and 614 and 618. 618 is a small shoulder to this 614 peak, and hence this complete peak is considered as to be one peak with a small shoulder, and this is because of FD0 to 7F2 transition. And similarly, you have 628 nanometer peak, which is nothing but 5D0 to 7F3. So similarly, the other complex, which is nothing but EU DMH fin, is also studied for emission spectra. If you can see here, the emission spectra was maximum for pH 7, which is considered to be the neutral. So the emission wavelength falls under red region, which is at 630 nanometer. And this is the XRD spectrum of that particular sample, the first sample. And you can see small peaks over here. So it's neither crystalline, completely crystalline, nor completely amorphous, because we have used a combination of organic and inorganic materials. And the same with the other complex also. And this is the FTIR spectra. And this FTIR spectra confirms the formation of the complex. And if you can see here, actually the characteristic peak of TTA is around 1,645 centimeter inverse. But we have observed the peak at 1,598 centimeter inverse. And this confirms the presence of TTA. And you have certain peaks at 1308 and 1184. And even we can see 1140. So these peaks are associated with carbon and fluorine, and which is a composition of this TTA. And similarly, N double bond C is observed for 1541 centimeter inverse and 1508, which confirms the presence of the other ligand. This is bipi. So similarly, for the other one also, we have confirmed the formation of the complex, the structural formation, and we knew that it doesn't fall under the nano range. Even then, we have carried out the same analysis, and we found that it is in the micrometer range, both of them. And the TGA and DTA have been carried out. So we can see the first week at 97.23 degrees centigrade, which is because of the evaporation of water molecules. And we have certain endothermic peaks at 221 degrees centigrade, and you have other exothermic peak, which is corresponding to the melting point. This can be considered at 329.22, and the end temperature is 366.15, and ultimately the weight loss was found to be 2.5 gram. And for the other complex, the weight loss was considered to be 3.5 gram. And when we have gone through the CIE coordinates, so the CIE coordinates generally depict how our natural eye looks whenever we perceive the light emitted by that particular complex. As I said, it's 613 nanometer, which means that it is under red region. So red region extends to a larger extent. So which color of that exactly is being depicted on this CIE diagram? And these are the coordinates. So this X corresponds to X coordinate. So how much is X and how much is Y? That is what is written for all pH values. And similarly, for the other complex also, we found that the emission is in the orange, reddish orange region. And these are the comparative results of the first complex and similarly the second complex. And later we have tried to understand what would be, what will happen if at all this complex is solvated in an organic solvent. Like if at all we want to coat it on a thin film, we need to mix it with a solvent. Since the complex, that's the phosphor, is in the powder form, if I want to coat it on a substrate, I want to make it a jelly sort of nature. And hence I'm interested to study if at all, if I add a solvent, is its PL intensity is going to change or not. So that is being carried out on various solvents, like we have considered chloroform, toluene, tetrahydrofuran, and acetic acid. So the molecular weight, these are the optical properties of that particular material. So if you can see the polarity index, more the polarity index, more will be the polar nature. And the refractive index, which is an important parameter in the study of optical properties, is also considered here. And we have taken the absorption spectra of these materials which are being prepared at different pH. And we have seen that at 7.5, the intensity is maximum for this DHF as well as toluene as well as the acetic acid. But in this case, maybe due to human error, we are not sure that at 7.5 we didn't get the maximum intensity, but at 7. But maybe because of the nature of this chloroform, if you can see the properties of it, it has chlorine, and you can see the molecular weight is also more. And among the polar solvents, its polarity index is also less. And hence we can consider that due to that reason, the chloroform has given less intensity. So now we have studied the same thing at different concentrations. The first case we have studied with the variation of pH, and in this case it's the variation of the concentration. We have observed the hypsochromic shift in the peak, which means that if I talk about hypsochromic shift, if at all, if your wavelength, initially it was 613 emission, and absorption, if at all, it is like we can see here, initially it was 380 here. The first peak, 10 power minus 3, it is 380. And for 10 power minus 4, if you can see, it has shifted to 357, which means that it reduced. It has shifted to the shorter wavelength. So that effect is known as hypsochromic effect, and the shift is known as hypsochromic shift. Similarly, if you see with the increase in with decrease in concentration, you can see initially the peak was at 380, and then shifted to 357, and then again shifted to 341. So with dilution of this, the peak has been hypsochromically shifted. So similar is the case with the other complex also, with the same complex with different solvent, that is phenol hydrofuran. We have considered another solvent here. Here also we have seen that the shift is towards the shorter wavelength, 367 in the higher concentration, 343 in the next case, and 333 in the next case. So similarly, in toluene also, if you can see the peaks, initially we used to get, in the other two solvents, we used to get two peaks, first one and the first and the second peak. But here we have observed only one peak in the first two concentrations, that is 10 power minus 3 and 10 power minus 4. But in 10 power minus 5 concentration, we have seen a peak with a shoulder. So if you can see here, the shoulder is at 357 and it is The first main peak is at 318. So this may be because the toluene has low refractive index when we have compared with the other solvents, and even the polarity index is less, and hence the other peak would have been missing there. So if you talk about acetic acid, we can say that it is polar protic solvent. Protonation is most common in that. Maybe because of the degradation, you can see that the intensity has drastically decreased whenever I have used this acetic acid. So we have also tried to find out the energy gap of the materials, and we have found that they are lying within the desired range, that is around 3 electron volts. So this is the energy gap of the materials which have the property to emit the red light. And we have even studied for the other complex also, that is bipi, for the different pH, and for different solvents like chloroform, phenyl tetrahydrofuran, this is THF. You can see that the concentration, if you see in chloroform, the intensity is maximum. And if you go for THF, you can see the intensity is decreasing. So what we tried here is which solvent would be best suitable and which solvent will not let the intensity to go down. That is what we have tried to understand, and we have found that the chloroform is the best suitable solvent to make the films, because after forming the film, the chloroform also easily get evaporated because it's volatile, and hence the film will be formed appropriately. So similarly, we have tried with toluene also, but we found that chloroform is the best one. And we have tried to study the Stokes shift, and Stokes shift here means if at all we are going for the absorption spectra and we are going for the emission spectra and the same graph, if you are plotting them on the same graph, then how this peak has been shifted, how longer this peak have been shifted. See, if you see here, the absorption spectra is around 300 and emission spectra is around 600. How far these two peaks are on the same wavelength range is a measure of Stokes shift. Okay, so more the Stokes shift, more will be the color. Suppose if the Stokes shift is left, maybe you'll not get the red emission. You may get green emission or the blue emission. So depending upon the requirement, as I said, the ability of absorption depends upon the energy gap of the material, and hence energy gap plays a vital role in the selection of the color. So these are the the conclusions of the results which you have obtained, and these are the solvents which we have used, and under this light, UV light, this is how we can see that particular liquid. So now for the other complex, we have carried out the same thing, and here also we have found that chloroform is only the best option. And with these results, we have confirmed that in solvents which are polar are more suitable for formation of thin films. And even we have tried to find out the energy gap of the materials. The energy gap was found to be a bit more in this case as compared to the earlier case. Still, they have given us a good result. And these are how we have obtained the PL spectra of the complex based on different pH. And even if you can see here, for different pH, here around 7 to 7.5 only the intensity is being maximum. If at all we increase the pH or decrease the pH beyond the neutral range, the intensity was found to be less. And here, if you see with the decrease in concentration, we have seen again the hypsochromic shift as if we have seen in the first case. And now the Stokes shift, the same thing as if we have got in the first case. And these are the results. And in conclusion, if you talk about when we compare these two complexes like EU TTA thrice bipi and EU DMH thrice fin, both are capable of emitting the light at 613 nanometer irrespective of the pH or the solvent which we have used. And we have excited these two materials, the complexes, we can say the first one with 381 and the second one with 372. And irrespective of polarity, they are very well compatible. And we have concluded that among all, the chloroform is the best one. And we have even prepared the blended films. So we have considered two different polymers like polymethyl methacrylate and the polystyrene. And we tried to make the thin films of it. And this is the procedure which illustrates the procedure to make the thin films. And ultimately, we got the film like this. And when it is exposed to ultraviolet light, this is how it looks. So even here, even after blending it with polymers, the intensity of that light has not changed, rather it has increased. Now let us go through the PL spectra. So before PL, we are going for UV visible spectra. So here, because of two different transitions, one is pi star transitions, we can see the peak which is in 200s, and because of the n pi transitions of the organic molecules, we can see the other band which is falling around 300. So now the films are prepared at different concentrations. We can say that different weight percentage, 10% complex, 25% complex, and this is the pure complex. If you can see, the intensity was around 0.6 for pure complex, and if you have added PMMA, and if you turn on the weight percent is 10%, the intensity has increased with the concentration. But if you further increase the concentration beyond 25%, we have seen that the quenching is happening, and we have stopped our results or the preparation of the films till 25%. So what I'm trying to say here is, so the intensity of this pure complex is less when compared with the intensity of the complexes which are embedded in the polymers. So thin film formation will not hinder the intensity, otherwise it is going to. On the other hand, or we can say unexpectedly, we have get the results in such a way that the intensity is more when we have doped with polymers, which is preferred. And we have carried out the same procedure to calculate the energy band gap, and we got around the same results, like in between 3 to 3.5 electron volts, which means that sorry, which means that even after doping with polymer, the energy gap has not changed a lot, but minor changes have been observed, but it is not going to affect the performance of that device. The same is with the other complex also. So the PL spectra, have been carried out for the films which are made with PMMA, and we have observed that with PMMA the intensity has increased, but on the other hand, when we try to use this polystyrene, the intensity has decreased, which means that PMMA is more preferable than PS if at all we want to make the blended films. However, the CIE diagram represents the red region which is going to emit, so color is being sustained. However, the intensity changes are being observed. So this is the summary of the blended films which we have done. So this is how it looks under UV light. And after thermal treatment, we have just seen how the intensity of this material is going to change whenever it is exposed to temperature. And we have seen that with the increase in temperature, the intensity has been decreased. So the optimum temperature which we can use, because the polymer has been added, so the optimum temperature which we can use is around 40 to 50 degrees centigrade. So for thin films, this is the graph for the other complex. And now we'll be going for some other color. These are in different solvents also we have done. I'll be speeding up. Okay. And let us go for, we have done with red light emitting phosphor, and now let us go for green and blue, because for solid state lighting, all these three colors are important. So for blue and green, we have used quinoline complexes because of certain reasons. So they have high electron mobilities. The thermal conductivity is good. They are thermally stable, and they are stable to moisture also. They even give a good photoluminescence, and they have good thin forming properties. They have good thermal stability. Glass transition temperature is also high, and they have good electrical conductivity. So the polyquinolines were first reported by Still and co-workers in 1970. Actually, they are categorized into two categories: polyquinolines and metal-based systems. So we have tried with this metal chelates of 8-hydroxyquinoline, which is generally quoted as MQ2. M stands for metal and Q2 stands for metal chelate, which is used as two times. Okay. So next, this is the structure of quinoline. Suppose this 8-hydroxy, it is hydroxy is added to the 8th position. We call it as 8-hydroxyquinoline, and we have used this 8-hydroxyquinoline in combination with different metals, and that is what I'm trying to show now. So we have used cadmium here, so to prepare CdQ2, and this is the synthesis procedure. So it's well explanatory, self-explanatory, we can say. So we have used 8-hydroxyquinone, 5 grams of it, and it's added to 10 ml of acetic acid and the double distilled water, and they are being mixed up on this magnetic stirrer, and this is being added to a certain quantity of cadmium nitrate, and this is going to form a combination. If you can see, the orange solution is obtained. Then 40 ml of aqueous ammonia is added dropwise into this particular combination of solution, and curd-like precipitate is observed, and it is filtered, and then if it is kept at oven around 45 degrees, you can get a pigment like this, which looks yellowish green, and this is how it looks under UV light. This is under ordinary light, and this is the UV source, and this is how it looks, and this emits the green light. And we have observed the excitation spectra, and this is the emission spectra, which is around 509 nanometer, which falls in the green region. And we have prepared some other complex like zinc ZnQ2. The same procedure has been adopted, and this is how we have obtained the zinc quinoline precipitate. And under UV light, we have made one more complex like Mgq2. So with Mgq2, you can see that when Mg is added, the intensity is a bit less in this case. And we have used 3 different solvents. Instead of using only acetic acid, we have used formic acid, and we have used DCM. And we found that DCM gave us a good result as compared with the acetic acid and the formic acid, because they are being the acidic media, and this not being. This is DCM is a polar solvent. And the same with the emission spectra. And there is one more important application apart from solid state lighting. As you know, the world is in search of novel materials. We want to replace the street lights, because these street lights are consuming around 3% of total energy with respect to lighting. And if at all you go for these lights, retro-reflective panels, and or even you have glass beads or LED markers, they are going to consume the light. So now what we have done is we have used that particular complex, and we tried to make a paint, and we will be carving it on the road, and it's going to emit light because of the phenomenon of phosphorescence. So that is what we have tried to do here. So we have taken the Mgq2 complex, and we have mixed it with toluene, and we have used a polymer. 2 polymers we have taken, one epoxy and the urea formaldehyde. We have painted the panel, and under the UV source, this is just a graphical abstract of it, and this is how actually we have coated on the glass slides, and this is how these panels look under the UV light. So this is bit greenish color, and this is bit like bluish. So if at all we are going to change the concentration as well as the resin which we are using here, the color might change to certain extent, and we can coat it on that particular surfaces. So we have even tested these panels tack-free, hard dry, whether it is going to stick to that particular substrate or not, whether it is water resistance or not. Chemical spray, we have sprayed a certain salt like NaCl or KOH, we have chemical effect. So is it going, this paint is going to sustain for certain longer period of time, even if the chemical is sprayed on it? That is what we have tested. And in few cases, we failed in justification, or we can say that in this particular chemical spray only, NaCl, whenever it is sprayed onto that, so there we have observed that dark spots have been developed over there. Otherwise, it's water resistance. It is in adhesive test also it has passed. In hard dry test also it has passed. In tack-free test also it has passed. So we need to work on that chemical spray test, and we need to come up with a solution about which chemicals are going to be friendly with that particular combination. So so we have till now we have discussed like LEDs, how they are made, and how on what mechanism they work, and how they are going to be different from organic light emitting diodes, and how these LEDs and OLEDs are going to be there for the purpose of solid state lighting, and even the displays. We have talked about fluorescent paints and even glowing dark paints. All these terminologies which we have studied in detail about are definitely going to help us in consuming less amount of energy, to save the energy, to save the environment. so that we can have a sustainable environment, and we are going to foster a sustainable and resilient society. So with this, I would like to end up my presentation. And if at all you have any queries, you are free to ask. Am I audible? Mhm. Because they are on the last day of STTP, maybe they are tired. Huh. You can even ask the questions on chat box. That is what I'm saying. Because this is the last day, maybe they became passive. Hmm. Susceptible to water. Yes, that is why we are going for encapsulation. Hmm. It will easily damage, and the problem is that the encapsulation process is also a bit hectic, and it's a bit costly also. So that is why if you talk about the OLED TV cost, it's going to be more. No, color contrast is good. Hmm. Lifetime is shorter because of the blue LEDs. Hmm. Hmm. White, red, and green. Yes. Huh, because of the cost only, they are not at commercialized to the extent which we all expecting. Till now. But on small scale, the LEDs are already there. On this mobile screens also, we have OLED screens, and watches also we have OLED screens. But only to the smaller surface area they are applicable right now. Yes, yes, yes. We actually made the OLED device also, but I didn't show those slides because already there were around 180 slides which I've made. So I thought like the time will be short, and hence I've deleted those images, the slides. How many participants are there? 66 are there. Hmm. Okay, then if questions are not there. New. Hmm. Hmm. So there are some. Nice session and very informative session. Excellent and interesting session. Nice session. Thanks. They're just talking on the chart. They're not even uh, orally saying. Excellent and informative session, ma'am. Thank you. So I got the messages, but they are not orally responding. Hmm. Okay. Yes, yes, yes. Yes, I have posted and even mobile number. Yes, I have posted my email ID as well as my mobile number also. Okay, thank you, Koteji, and all participants for your kind attention. So, can I leave now? Okay, okay, thank you.